Okay, I think we'll get started. So this is just a preliminary video in this series on the PIC12F675 microcontroller. And we will go through an overview of the datasheet and then an overview of what are the features of this particular microcontroller. We'll compare and contrast this to the PIC10F200. So if you've gone through that series of labs, you'll be familiar with some of the capabilities of that. And we'll see that this is a more capable microcontroller, although still quite a small unit. The PIC10F200 lived in the class of families called the baseline PIC family. We take a step up now to the mid-range, still 8 bits in terms of the instruction sets and so on. Still 8-bit mid-range family. 6 digital I/O pins as compared to 3. And then some new features, comparator and an analog to digital converter, 10-bit, and some EEPROM memory, and also some interrupts. So we'll be looking at these features in addition, primarily focusing on these features because the digital I/O stuff, a lot of that will transfer directly from the PIC 10F200 series that we might be finished with. And if you haven't done that and you want to get into a little bit more of the digital I/O, you can follow some of those videos after you've completed this series as well. All right, so we're going to jump into the data set, the data sheet. If you did take the earlier course, you'll notice I went through that data sheet maybe in a little bit more detail than I will today. Part of that is, one, it's early and you haven't really worked with the chip yet, so it's to go into a lot of detail is maybe not as beneficial. Also, with all this new stuff, it's a lot all at once. So as we work through different experiments to deal with each of these, then we'll bring up those parts of the data sheet as well. All right, so with that, let's switch over to the data sheet here. So I'll go to the doc cam. Okay, so I would suggest, definitely suggest printing this off and following along. Some of this is going to be hard to see on this screen, and furthermore, you'll just want to have the data sheet with you when you're programming. It's completely free. You can get it from Microchip, or you can get it from Microchip, or you can get it from DigiKey or other places as well. It's fairly long. I think it's like 130 pages. I deleted a bunch of pages, but it's still, I think, 81 pages that I printed off. If you're good at or prefer to use a PDF, that's great. I'm, I guess, older, so I still like, in documents like this, it's nice for me to have a sheet of paper to refer to. And I feel like I use it a lot, so I think it's worth printing off. All right, let's just start with the kind of a basic outline. So some of the stuff that I mentioned on the board there, but some new stuff here. So it has an internal clock, and we will just use the internal clock. Good exercise, I suppose, to make circuits with an external clock, but we will use the internal clock. 4 megahertz, which is the same as the PIC 10F200. So a lot of our delay sequences will be the same, so that's kind of handy. Some flash and EEPROM, so we'll work on, probably do a lab writing to that. It might be a bonus lab, so we'll get a little bit of familiarity there. That always has to be referenced with indirect references, so we'll have to review that a little bit, but we did do that in the PIC 10F200 sequence, although not with EEPROM. Analog comparator, so in terms of lab use, very functional, both comparing two voltages, one to another, or comparing a voltage against a reference. So we'll be doing some labs there. Some analog to digital conversion. 10-bit is okay. It's not a 16-bit, of course, but better than an 8-bit, so not too bad. All right, this has an 8-pin mounting jacket here in this dip configuration, and so positive 5 volts, although I think it can take 2 to 5. We'll use positive 5 volts. Ground. Pin 0, 1, 2, 3, 4, 5 are digital, can function as digital inputs, also as analog inputs for many of these, for the comparator and for the analog digital converter. So some good stuff there. Let's look at the memory structure of these registers. So there's 2 banks, and there are important registers on each bank. So for example, the program counter is on bank 1, that's over here. This is bank 0. Status counter is in bank 0, GPIO in bank 0. Some of these are in both, so we'll have to do some switching back and forth, and that's done through the status register. We have these two are the CM-con and the VR-con are the comparator configuration register and the reference voltage reference for the configurator for the comparator. The ANCEL and these AD cons are for analog to digital conversion as well. So we'll be utilizing these registers. Then there's just the general registers that you can write to and read from, like you can with the PIC12F675, but more of them. And in addition, some EEPROM. Okay, so let's kind of just summarize some of the important registers. So INDF register, that is for indirect file reading. The program counter is the PCL register. Status, this gives us a lot of flags. So when we're doing arithmetic, for example, our digital digits carried. Also, this RP0 is what bank we're on. So that's how we change from bank to bank right here. FRS is associated with the NFDR for indirect file, so for pointers and stuff. We won't really do that here like we did with the 10F200, but when we do the EEPROM stuff, you do have to do indirect file measurements. 6 pins here for the GPIO, so how we can define those as input, output, or how we write to these, whether externally as an input or an output. And then the TRIS, actually the TRIS is not shown on here. But yeah, because that's not a physical register. But that's then how we assign these then as input and output. Interrupt register here, and then this comparator register as well, and the A to D register down here. Over here. Oh yeah, here's the TRIS. Okay, so TRIS is over here. This apparently, I think these are just direct copies of the program counter and the status register. And then VRCon over here, and these are some EEPROM registers for reading and writing to the EEPROM. So some key special registers, more of them. I think there like 8 or 10 of them for the PIC12F200. So more to get a handle of for this for sure. Interrupts, won't say too much here right today. There's a global interrupt that turns everything on or off, and then there's some different types of interrupt, peripheral and GP2 interrupt, and then some port change interrupts, and so that's for utilizing interrupt protocols. And then let's look here at the GPIO ports. Important thing here, in the TRIS, we set a 1 if we want it to be an input and a 0 if we want it to be an output. Another important thing that we'll see in the code is that the AND cell and the CCOM must be initialized to configure an analog channel as a digital input. So if they're not configured, then the digital I/O, even though we're not using the analog to digital or the comparator, won't work. And so we'll go through that more carefully when we write some code. All right, comparator. So the important parts of the comparator, these last 3 bits are what choose the type of comparator, and we'll look at that in just a moment. This bit, whether we have the inverted or non-inverted output from the comparator, and then this is the comparator output bit. Importantly, what we see here, the last 3 digits of the last 3 bits from here, so these last 3 bits are what determine the nature of the comparator. So most often we would use in the lab, we'll do 2 labs. We'll do a lab that goes through both of these 2 types. One is the just the comparator with output. So we have 2 analog inputs, and then the output is either on or off based on which is higher. And so that is a comparator with output. And then we'll have a comparator with output and internal references. And so that will be this. So these 2 indicate for that. And then this up here, this is important actually. It seems like, what in the world is this? Nothing is going on here in terms of the comparator, but what this does is it initializes those pins as being digital input pins. So we have to choose this configuration of the CMCON if we want to use them as just digital input-output pins. Let's see, I think that's about it there. Analog to digital conversion. This is kind of a process here. So I think it's good that we'll go through this, but then I think eventually we'll want to move towards a dedicated analog to digital converter that then can communicate with one of the communication protocols with the microchip. But good to see how it all works. It takes a number of clock cycles to cycle this through, and we'll do a couple of labs that help us understand how that all works. And I must say that there's some pretty good, although we'll need to supplement this, instructions on how to utilize the analog to digital converter there. Similarly, I'm not going to say much about the EEPROM stuff right now, but very strict rules on how to implement the code. And so when we talk about reading, writing, and verifying the EEPROM, particularly for the writing side of things, things have to be done exactly like what's in the data sheet. So it'll be good to be aware of that in the data sheet. And last thing that we'll talk about then is the instruction set. And so what's really cool, I think, about the PIC microcontrollers and working in assembly is that it's a very limited instruction set. So I think it's like 33 or 34 instructions total. So you feel like you have some hope of getting your mind wrapped around all those different instructions. And then the fun puzzle is how do you put together algorithms that don't have for loops and while loops and all that, in using just these instructions. So I think that's kind of cool. And then also very, very close to the ones and zeros of the machine code. So you can actually see the machine code over here or what's called the opcode for each of the different types of instructions. There are basically 3 categories of instructions: byte-oriented instruction, bit-oriented instructions, and literal and control instructions. So the byte is working with a whole register, so 8 bits. So this would be like moving things to the working register, moving things to a storage register. The acts of adding, subtracting, those are done byte-wise. The bit-oriented is where you really start talking to the devices, your peripherals. So if you're in a science laboratory, talking to the external world is so important, and that's done with clearing and setting bits. So you're communicating via the bits, so that's important. And then we need to do several things like branch, so go to, call, also work with numbers, so those are called literals, and then also return from these calls. All right, the nice thing about the data sheet is that the instruction set, then in addition to that summary, which has kind of the basic structure here on how to use it, but what's nice is in the data sheet you can find every single one of these, and then how it's used. So that's really handy when you're trying to put together some of your own ideas for algorithms. All right, so that's a little cruise through the data sheet. Again, I would definitely suggest that you print that off and have it with you as we work through these various labs, and then as you get on to some of your own projects.